Welcome. In this explainer, we're going to crack the code of matter itself. We're going to take what feels like a simple vocabulary list and turn it into this incredibly powerful tool for understanding, well, pretty much everything.
I mean, really think about that for a second. What if there was a single cheat sheet that let you predict how the fundamental building blocks of our universe are going to act? Well, guess what? That cheat sheet is real. And by the time we're done here, you're going to know exactly how to read it.
Okay, so first up, the atomic blueprint. Before we get to the big picture, we have to start small. I mean, really small. We're talking about the atom, the basic building block of literally everything. Now, there's not just one type of atom, right? The different flavors are what we call elements. The best way to think about them is like letters in an alphabet. You know, with just 26 letters, we can make every word you can imagine. Well, with just about 118 known elements, the universe builds everything.
So how do you tell one element from another? It all comes down to one thing, the atomic number. And here's the key thing to remember. The atomic number is only the number of protons. That's it. It is the atom's unchangeable, unique ID. If it has 6 protons, it's carbon, period. If it has 7, it's nitrogen. There are no exceptions. This is what defines it.
But wait, there's more. In that little core of the atom, besides protons, you've also got neutrons. And if you add the number of protons and the neutrons together, you get the mass number. It's basically just what it sounds like. It tells you how heavy the atom is. It's really that simple. Okay, if you're studying for a quiz, this right here is something you've got to nail down. Atomic number is the ID. It's who the atom is, and that never, ever changes. The mass number is its weight, and as you're about to see, that actually can change. So one tells you what it is, the other tells you how heavy it is.
So you're probably asking, wait, how can the weight change if the ID is locked in? Great question. And the answer is isotopes. Isotopes are just atoms of the exact same element, so they have the same number of protons, but they're carrying a different number of neutrons. You've probably heard of carbon-12 and carbon-14. They're both carbon, right? Because they both have 6 protons. But carbon-14 just has 2 extra neutrons, which makes it a little bit heavier.
All right, now for the ultimate cheat sheet. Because all these different elements, they're not just a chaotic mess. They're organized into the most beautiful, most powerful cheat sheet in all of science, the periodic table.
So the whole table is laid out in rows and columns. The rows going across are called periods. As you read from left to right, the properties change in this really predictable pattern. But the columns, the ones going up and down, those are called groups or sometimes families. And that's where the real magic is. See, elements in the same group are like siblings. They have super similar personalities and they behave in really similar ways. And you can see that right here. Just look at that row going across. That's a period. But then look at the column going down with fluorine and chlorine. Because they're in the same family, you can bet they're going to react in very similar ways. Just knowing an element's group is a massive shortcut to figuring out how it's going to act.
So why does this work so perfectly? I mean, why do elements in the same family act so much alike? Well, it all comes down to a few key things that give each element its own unique personality. And the single most important part of that personality, it's the valence electrons. These are the electrons way out on the edge, in the atom's outermost shell. Think of them like an atom's hands. They're the part that actually reaches out and interacts with the world. They determine literally everything about how an atom is going to react. But how tight of a grip does an atom have on those all-important outer electrons? Well, that depends on something called the shielding effect. Imagine this. The positive nucleus in the center is trying to pull all the negative electrons in, but the electrons on the inner layers, they kind of act like bodyguards. They get in the way and block or shield those outer electrons from feeling the full magnetic pull. So the more layers you have, the more shielding you get. And all that shielding has a direct effect on the atom's size, which we call its atomic radius. It's just what it sounds like, a simple measurement from the center to the edge. And it makes sense, right? The more shells an atom has, the more shielding it has, and the bigger it gets. Now let's talk about ionization energy. Think of this as the cost to steal one of those valence electrons. If the nucleus has a really strong grip, meaning not a lot of shielding, it's going to take a ton of energy to rip an electron away. That's high ionization energy. But if that grip is weak, hey, the price is low. Electronegativity is kind of the opposite. It's not about how well an atom holds onto its own electrons, it's about how greedy it is for someone else's. It's a measure of how strongly an atom pulls other electrons towards itself when it's trying to make a bond. Some elements, like fluorine, are incredibly electronegative. It's the greediest element of them all. And here is the big aha moment. It's all wrapped up in something called the periodic law. It basically says that because all these personality traits, the size, the energy, the greediness, change so predictably across the table, an element's location tells you everything. You can predict how it's going to act without even running an experiment. Its address on the table tells you its whole personality.
Okay, so we've got the personalities down. Now, let's see how those personalities lead to action. This is where the chemistry really happens, where atoms start to interact, to bond, and to build the world we see.
See, most of the time, an atom is neutral. It's got the same number of positive protons as it does negative electrons, so everything's balanced out. The overall charge is 0. But if that balance gets thrown off, if it gains or loses an electron, it's not neutral anymore. It becomes an ion, which is just a fancy word for an atom that has an overall electrical charge.
And there are two main types of ions. If an atom gains an extra electron, it now has more negative bits than positive ones, so it becomes a negatively charged ion called an anion. If it loses an electron, it's left with more protons, so it becomes a positively charged ion, which we call a cation. Here's a little pro tip for you. Anion is a negative ion, and the T in cation looks like a little plus sign for positive.
So why are atoms bothering to gain or lose electrons in the first place? Well, they have one ultimate goal: to form chemical bonds. A bond is just the force that holds atoms together. And this is how we get molecules and all the amazing compounds that make up our world. And it is all driven by those super important valence electrons.
So let's put it all together. The crucial point is this: an atom's desire to react is a mix of everything we've talked about. Atoms are happiest, they're most stable, when their outer shell of electrons is completely full. That's called a full octet. So how it behaves depends on everything. Does it need to give away just one electron to be stable? Or is it super greedy because it only needs to grab one more? All these personality traits decide what it's going to do.
And that really brings us back to the single most important idea of this whole thing. An element's address on that periodic table tells you its entire life story. You know its size, you know its personality, you know its family, and you can predict what it's going to do next. It is the ultimate chemical storybook.
So if we know the rules, if we can read this chart and predict the future for every single ingredient in the known universe, what does that mean we're capable of building? What new materials, what new solutions can we create? That is the incredible power that comes from cracking chemistry's code.